Good evening, everyone. Welcome to O-Level Physics. Today, we'll be starting on the new topic on turning effect of forces. Okay, today is Monday, 17th of April, 2023. Okay, my name is Mr. Chu, and let's begin. Okay, I'll be showing you all the mind map of the old syllabus. Okay, so you can see over here, this is the old syllabus mind map. We skip this topic, mass, weight, and density. Okay, because this topic has been absorbed into dynamics and pressure. So you'll be going straight into this topic called the turning effect of forces. Okay, so this is the old syllabus mind map. But a lot of things that you all learn will be the same. Just that they are just reconsolidating the theory, the concept, the topic into lesser topic. And there's a new topic that you're going to learn in this new syllabus, which is nuclear physics. Okay, you're going to learn the nuclear physics. It was in the syllabus during my time as a student. Okay, and then it was removed when I was a teacher. And then this year, it is being introduced back for you all again. Okay, so nuclear physics will be the next branch, a new branch here. It'll be just one topic. So you're going to learn about radioactivity, about half-life, and so on. Okay, so that will be the new branch that is going to learn in the new topic. Let me go and revise this mind map for the new topic, right, for the new syllabus. Okay, so we'll be touching on the turning effect of forces. Previously, we are talking about dynamics. Okay, before I begin, can you all tell me your understanding of what dynamics is about? Okay, can you all tell me what you understand about dynamics? Okay, I write down in your chat, what do you understand by dynamics? Okay, what do you understand by dynamics, everyone? Okay, Rui Hong, very good. Okay, how about Hao Ming and Zachary? Yeah, what do you understand about dynamics? Okay, Hao Ming, what do you understand about dynamics? Okay, before I talk about the effect of forces. Okay, what do you understand about dynamics, everyone? Yes, force. But basically, everything in this green branch are all talking about, maybe to a certain extent, talking about forces. Okay, mechanics is about forces. So what does dynamics actually talking about? Okay, then dynamics actually basically means how force affect motion. Clear? Okay, so force can force actually when there's a net force on an object, on a mass. Okay, when there's a net force on a mass, the mass will undergo acceleration. Okay, so that is the whole big topic about dynamics. Okay, when a force affect a mass, the force is applied to a mass, that mass will undergo acceleration. Okay, meaning that the motion will change. Okay, when I say motion change, it means there is no acceleration. There is acceleration. Okay, when there is no change in motion, it means If it's at rest, you remain at rest. If it's moving, you'll remain moving in the same speed, in the same direction. Okay, that's the meaning of no acceleration. Okay, so dynamics actually teach us forces actually will affect motion. Okay, you actually create acceleration to the mass. Okay, so now we are going to talk about the next topic called the turning effect of forces. Okay, so basically what does this topic means? This topic we're talking about force can make things turn, okay, or rotate. Okay, make things turn or rotate. Okay, in the chapter 2 or chapter 3, dynamics, we're talking about force can make a mass accelerate. Okay, so now we are talking about force making an item to turn or to forces can also create a turning effect. Okay, you can actually make something turn or rotate. Okay, so that will be the main part of this topic. Any questions so far regarding topic number 4, turning effect of forces? Okay, Zachary, you understand where what I'm trying to ask you? Dynamics is where forces will produce acceleration to a mass, whereas turning effect of forces is forces can cause a turning effect on things. Understand so far? Okay, let's continue. Okay, so basically this topic I'll be going through 3 main things. Okay, we are talking about how things turn. Okay, how things turn. Okay, how we balance all the moments. Okay, how we balance all the moments. So every moment itself will actually cause a turning effect. Okay, so when all the moments is in equilibrium, the whole thing does not turn anymore. Okay, does not turn anymore. Okay, so we also talk about the theory of the center of gravity and stability. What factors affects stability? Is that clear? Okay, so let's begin. Let's begin. Let's talk about moment of a force about a pivot in terms of event. Okay. We talk about the formula first. We talk about formula first. Okay, so the formula of a moment of a force. Okay, moment of a force is how a force causes things to turn. Okay, whether you turn or not is called moment of the force. The turning effect of a force is called moment of a force. Okay, the formula is force times perpendicular distance from the pivot. Okay, and for moment, okay, I need you all to understand when there is a moment, it's either a clockwise moment or an anti-clockwise moment. I repeat myself again. If there is a moment, it's either a clockwise or anti-clockwise. Okay, that's what you need to learn in secondary school when we just doing all 2D. Okay, 3D will be different thing But based on 2D, on the 2D plane, when you have applied a force on something, if there is a moment, you either have a clockwise moment, your item will either turn clockwise or you will turn anti-clockwise. Is that clear? Okay, wait, I draw wrongly. This is not anti-clockwise. Okay, anti-clockwise like this, anti-clockwise. Okay, so I draw wrongly just now. Okay, so a moment of a force. Okay, a force can cause something to turn. Okay, when it causes something to turn, it's called moment, and that moment can be clockwise moment or anti-clockwise moment. Okay, so that is the idea of moment. Okay, so I want you to first think what is moment. Moment means something is turning. Okay, so a force can cause something to turn. We call that moment. The moment can be a clockwise moment or an anti-clockwise moment. Is that clear? Then let me just go through some example. Okay, so basically, forces beside able to change the speed or direction of a mass. Okay, in chapter 3, we learned that in dynamics, force can change the speed of a mass or change the direction of a mass. Okay, so in this chapter, we are talking about force can also cause something to turn. Okay, it can also cause something to turn or rotate. Is that clear? It can cause something to turn or rotate. Okay, so let me just go through moment, which is just A and B. Let me find some example for your. Hold on. Let me find the example. Okay, let me just do a simple drawing. Okay, so we know there's this door. Okay, there's this hole where there is a door. Okay, the door, there's a knob. Okay, there is a hinge on the door. Okay, so the door can turn in and turn out. Is that clear? So if you were to give a push on the knob, okay, so what happened? The door will turn this way. Am I right? Okay, so this way, you could turn this way about the pivot, about the hinge. Is that clear? Okay, so the force that you apply on the knob, okay, cause a turning effect on the door. Okay, so this is called the turning effect of force. Okay, so in this topic, we are going to measure how great the turning effect is, or how big or how small. Okay, so in this case, there need to be a pivot. Okay, you need to apply a force, and the force has to be away from the pivot. Up to here, any question? Are you clear about this? Okay, up to here, you need to apply a force. The force cannot be applied on the pivot. It must be away from the pivot. And therefore, it will create a turning effect on this item here, which is the door. Okay, so are you clear what I'm saying so far? Okay, a force can cause something to turn. Okay, the term that we are going to learn here is the turn is called moment. Okay, the moment. Okay, so one of the everyday example is opening and closing of the door. Is that clear? Okay, so if you understand up to here so far, okay, you are able to appreciate that a force can cause something to turn. Example like opening and closing the door. Okay, give me a yes reaction. Thank you, Ray Hong. Thank you, Zachary. How many you okay? All right. Okay, so let me explain in detail on this formula on the moment. Okay, so let me explain more in detail. Okay, so let's give an example. Let's look at this example here. Okay, let's look at this example. That number one, there has to be a pivot. Okay, number one has to be a pivot. Number two, there has to be a force away from the pivot. Okay, away from the pivot. Okay, so before we go into calculation, when we apply a force on this line, are you all convinced that this thing will turn anti-clockwise? Are you all convinced that this thing, let's say this is a plank, it will turn anti-clockwise around the pivot? Okay, if you are convinced, give me a thumbs up. If you are convinced that you can turn anti-clockwise, give me a thumbs up. Okay. So are you all convinced? If I apply a force away from the pivot, in this example, you'll cause this thing, okay, this thing with a length of D to turn anti-clockwise. Is that clear? Okay, so the next concept you need to know is you need to draw the perpendicular distance. I repeat myself, the perpendicular distance from the pivot, okay, from the pivot to the line of force. I repeat myself again, the perpendicular distance from the pivot to the line of force. Okay, so this distance, this D, has to be perpendicular to the line of force. Is that clear? Yeah, I'll give a few more very confusing example, but I want you all to know this D joins the pivot to the force, and this D has to be perpendicular to the force. Are you all clear about this so far? Okay, if you understand this, give me a yes reaction. Hello. If you understand, give me a yes reaction. Thank you, Zachary. Ray Ho, how many are you clear? Okay, thank you, Hao Ming. Ray Ho, are you okay? Okay, since you all tell me you all understand, I will draw a different force. Then you all tell me where is a perpendicular distance. Okay, so let me erase this thing. Yeah, erase all these things. Now, if I were to apply a force, maybe like this. I apply a force like this in this direction. Okay, this plank is still the same length, but can you tell me what is the perpendicular direction? Okay, Hao Ming, would you like to try first? On the chat group, sorry, not on chat group, on the screen, can you actually draw the perpendicular distance of this example, where the force is in this angle? Okay, very good. Ray Ho and Zachary, you understand about this? Okay, so this distance in the purple will be the perpendicular distance. Clear? Okay, so moment, we can use the formula tau. You know, symbol tau. Okay, we can use tau for the symbol of moment. Actually, tau doesn't represent moment. Tau actually represents torque. T-O-R-Q-U-E. Okay, so we can actually interchange the word torque and moment. Okay, so now we just say that torque. Okay, this tau actually can represent moment. Okay, so tau, the formula will be force times the perpendicular distance. Is that clear? Okay, so to find how much it can turn anti-clockwise, you just need to multiply or to find the product of the force and the perpendicular distance here. Is that clear? The force and the perpendicular distance here, when you multiply them, you'll be able to calculate a value. The value actually is the moment of the force. Clear? The bigger the moment, the greater the turning effect. The smaller the value, the smaller the turning effect. Is that clear? Everybody understand this concept so far? Okay, and because there is two directions, either anti-clockwise or clockwise, also write down that this is actually anti-clockwise. Okay, so in this case, same thing. To find the moment or the turning effect of this force, you just need to write down tau is equal to force times d. Just to have a reminder, you can put a perpendicular sign there, unless you remind yourself that this d has to be perpendicular to the force. Clear so far? Okay, so it's very simple to find a moment of one force. Okay, things get complicated when you need to find moment of many forces. Then you need to do calculation. Okay, y'all give me a second. Let me increase my aircon. Very hot. Okay, so far you're clear? Okay, so I give the second example on the right side here. You have a force acting downwards. This force is not acting on the pivot. So there is a perpendicular distance from the pivot. Okay, so this force will cause this line to rotate clockwise. Okay, so this in this example, you'll cause it to turn clockwise. Is that clear so far? Okay, so you understand now you understand simply how a force can cause the thing to turn. Okay, so let me introduce the formula now. Okay, so this moment of a force, you can use tau if you want, is force times perpendicular distance. And this perpendicular distance, I like to put the perpendicular sign there. At least it reminds me. Okay, and what is the unit for force? The force unit is in Newton. The distance is in meter. Okay, so Newton and meter. So the unit for moment of a force will be Newton meter. Is that clear? Okay, it is a vector quantity because there is a direction. Okay, the direction is either clockwise or anti-clockwise. Understand? Okay, up to here, are you all clear about this? Okay, so let me ask you a question. You tell me, is it true or false? Okay, a force always causes a body to turn or rotate. Okay, so can you tell me, is this true or false? A force will always cause a body to turn or rotate. Is that true or false? Okay, give me a yes or no reaction. Okay, what I say, is it true or false? Okay, Ray Hong say false. How about Hao Ming and Zachary? Okay, Zachary say false. How about Hao Ming? Your device no battery again. Okay, so a force will not always cause a body to turn. Why? If I apply a force at the pivot, example like this, If I apply a force at the pivot here, like that. Okay, exactly at the pivot, the thing will not turn. Okay, the thing will not turn because moment is equal to force times distance. Yes, there is a force, but if the distance is 0, you will get no moment. Is that clear? Okay, so if there is no perpendicular distance to the pivot, okay, there is no distance, there will be no turning effect. Okay, so this statement is not correct. Okay, if a force is acting on the pivot, the thing will not turn. Is that clear? Okay, so another example, I have a seesaw. If I apply a force anywhere here, okay, it will turn. Okay, it will cause it to rotate. Okay, but if you were to stand exactly at the pivot, okay, if you were to stand exactly at pivot like this, okay, the thing will not turn. Is that clear? Because the perpendicular distance d is 0, so your moment will also be 0. Is that clear? Okay, so I finished talking about the concept of moment, how things will actually turn. Okay, so I finished talking about moments. Okay, I talk about how a moment, okay, how do you actually get a moment of a force about pivot? Okay, we also talk about moment of a force or torque. Okay, the formula is force times perpendicular distance. Okay, up to here, any question for me? Up to here, any question for me? Okay, let's go back to the example of the door again. The hinge is here. This is your door. Okay, this is your door. Okay, this is your door. Now, to make the door open and close easily, where will you place your knob? Will you place it at A or B? Okay, type out your answer in the chat and then explain why. Will you place it at A or B? At A or B? Where will you put your knob? Hello? Will you place your knob at A or B? Okay, Hao Ming say B. How about for Rui Hong and Zachary? Can you explain the reason why? Okay, Zachary say B. Can you give me the reason why? How about Rui Hong? Okay, we also say B. Can you tell me the reason why? Why you all chose B? Why did you all chose B? Okay, I use the same formula lah. Okay, given the same moment, the same turning effect. Okay, given the same turning effect, A. Okay, A has a perpendicular distance of from here to here. Okay, then B has a perpendicular from here to here. So given the same T, if your perpendicular distance is high, the amount of force you need to open the door will be low to achieve the same turning effect. Is that clear? So if you put your doorknob further away, your perpendicular distance is greater, so you just need a smaller force to create the same moment, the same turning effect. Is that clear so far? Okay, if you understand this, give me a yes reaction. Okay, now I'm going to give you another example. I'm going to give you 3 ways I'm going to push the door, to close the door. Okay, I'm going to give you 3 ways to close the door. Number 1, this way, and this way. Okay, this is 90 degree. This is 45 degree. And this is 60 degree. Okay, X, Y, and Z. Which way will you do to push the door, to close the door? Will you use force X in that direction, force Y in the direction, or force Z in this direction? Okay, which way will you choose to close the door? Which way? A, B, X, Y, or Z? Okay, Ray Hong says force Y. Okay, Zachary and Hao Ming, will you choose X, Y, or Z to close the door? Okay, Zachary will choose Y. Okay, let me change color. Let me change color. X and Z. Okay, X I go in this way. Z I go in this way. Okay, so for green color, okay, the perpendicular distance, okay, from B, the perpendicular distance from B to the ledge will be like this. Okay, this is your perpendicular distance. Now, what is the perpendicular distance from the red color force to the pivot? Okay, it need to be perpendicular to the pivot. Okay, so the perpendicular distance here, okay, in this case, this is the perpendicular distance. Okay, then for the red color, where will the perpendicular distance be? It will be from here to here. Okay, it need to be perpendicular to the force. Okay, how about for Z? Okay, for Z, you need to extend the line further. Okay, hold on. You need to extend the line further. Okay, you need to extend the line further. Then you need to draw the perpendicular distance to the force. Okay, so that it is 90 degrees here. So can you see the green perpendicular distance is the greatest? So this force Y can be the lowest to produce the same moment. Is that clear? Whereas you see the red color force has a smaller distance. So the distance here is smaller. You will need a greater force to close the door at this angle. Okay, you understand where am I coming from? I'm trying to actually play around with the direction of the angle of the force to show that the most effective way to close the door is where your perpendicular distance is on the object. Is that clear? If your force is not perpendicular to the object, your perpendicular distance is now shorter. You will need a greater force to produce the same moment. Okay, Zachary, your no is for what? What are you talking about for no? You're thinking of something else, right? Okay, so are you clear about this example about closing door? Why you need to push at the perpendicular to the door? You'll have easier to close the door, and why the knob should be as far away from the hinge as possible to make closing of the door easier. Are you clear about this? Okay, so now we are going to go to the second part. Okay, we are going to the second part. We are talk about moments. Okay, so the next thing we're going to talk about will be equilibrium. Okay, so we're going to talk about these two things. Okay, what is okay, the main thing that we're going to talk about will be this thing called the principle of moment. Okay, this principle of moment, all of you need to memorize. Okay, all of you need to memorize. So what is a principle of moment? Okay, let me write that down now so that you all can memorize. Okay, so the principle of moments state that when a body is in equilibrium, the sum of clockwise moments about a pivot is equal to the sum of anti-clockwise moment about the same pivot. Okay, this is something that you need to know. Okay, the easy thing is like this. Principle of moment, right? The easy way of explanation, let me just explain to you. The easy way of explaining this is just that clockwise moment, okay, the sum of clockwise moment is equal to the sum of the anti-clockwise moment. Okay, so this is basically the principle of moment. Are you all clear about this? The sum of all the clockwise moment is equal to the sum of all the anti-clockwise moment. If that is true, the body will be in equilibrium, meaning that it will not turn. It will not turn or rotate. Clear? Okay, so a principle of moment for a body, you need to say that for when a body is in equilibrium, the sum of the clockwise moment about a pivot is equal to the sum of anti-clockwise moment about a same pivot. So this is the formula that I'm talking about. Okay, so you need to just, this concept is easy, right? If all your clockwise moment is equal to all anti-clockwise moment, then the thing will not turn. Does it make sense? Okay, one more thing to take note. We must be using the same pivot. We cannot be using a different pivot. Okay, I'll give an example. Okay, I give an example here. If I have a seesaw, okay, I have a pivot here. Clear? Then I got different forces. So my clockwise forces, I will use red. Okay. Okay, wait, wrong zipper. Okay, this will cause the thing to turn clockwise. Okay, this will cause it to turn clockwise. Okay, so these three forces will cause it to turn clockwise. Am I right to say that? Now I use green to show. Okay, so these green forces will cause the thing to turn anti-clockwise. So when we measure the moment, okay, let's look at the first one, the first red one. Let's look at the first red one. Wait, sorry, wrong. Let's look at the first red one here. Okay, we have to find the moment caused by this force by multiplying the distance to the pivot. Okay, so it must be the same. All must be to the same pivot. This one and this one as well. Are you clear about this? Okay, you must be using the same pivot. Then when we calculate the anti-clockwise moment, it's the same thing. We must use the same distance here as well. Understand so far? Okay, so we must be using only one pivot. We cannot be using many different pivots. Okay, so for a seesaw question, the pivot is very clear. Okay, it's very clear. So why do we need to say same pivot? Okay, because there are some questions that is not so clear. Okay, so for the seesaw, okay, for the seesaw like this, are you clear that all your forces must be measured to only the one pivot for both clockwise and anti-clockwise moment? Okay, so are you clear about this? If you're clear about this, give me a yes reaction. Then I'm going to give you a second example that is not so clear. Okay, if you're clear about this, give me a yes reaction. All your moment has to be to the same one pivot. Okay, Zachary, understand. Ray Hong and Hao Ming, understand? Ray Hong and Hao Ming, are you clear? Hao Ming, okay? Okay, Hao Ming asked a question. The unit of moment is NA. That is correct. Okay, the unit is Newton meter. Okay, that is very correct. Okay, so I'm going to give you another example that is not so clear. Okay, not so clear on where is the moment. Okay, sorry, where is the pivot? Okay, let me give another example. Okay, we talk about swing now. Okay, we talk about childhood stuff. Just now we talk about seesaw, right? How about we have a swing like this? Okay, we have a line pulling on top here. Another line pulling on top here. Correct? Now, where is the pivot? Where is the pivot? If the whole thing is not moving, where will the pivot be? Okay, so in this case, for example, this bench here will have a weight. Okay, this bench here will have a weight. Hey, hold on. Why become like this? Oh no. Hey, the drawing has disappeared. Okay, let me draw again. Okay, we have a seesaw. Sorry, not seesaw. Now we're talking about a swing. Okay, so we know that this swing has a weight. Okay, has a weight. So how do we draw the weight? Okay, this middle of this swing, there's a weight that's going down. Okay, so there's a weight. There's a weight here. Clear? And this swing, there will be two tension pulling you up. Okay, so if we were to talk about the total force, W should be equal to T1 or T left equal to T right. Okay, so if the whole thing doesn't move, it stays down there in equilibrium. Okay, the weight should be equal to the tension on the left plus tension on the right. Okay, this one you all know. Okay, this one you all know. However, okay, however, how do we use turning effect? Okay, remember just now I mentioned, okay, let me write down the whole definition again. What is important? So the principle of moments state that okay, when a body is in equilibrium, the sum of the clockwise moment about a pivot. Okay, remember I was talking to you about the pivot itself is equal to the sum of anti-clockwise moments about the same pivot. Okay, so now we are focusing on the pivot and the same pivot. So we need to decide, we need to set one point as a pivot. So for example, I let this point be the pivot. Okay, I let okay, because this T left, okay, this T left is acting on the pivot. This tension will not cause this bench to turn. Is that clear? This tension acting on this pivot will not cause the bench to turn. Now, if I were to talk about the weight, okay, this weight, only the weight, we don't care about the other two. The weight is acting on the right side of the pivot, acting downwards. So the weight will actually cause the bench to turn clockwise. Are you convinced about it? The weight about this pivot will cause this bench to turn clockwise. Are you clear about this? Okay, are you clear about this? Next, we talk about this tension on the right. So we use this tension on the right based on this pivot. This tension on the right by itself will cause the bench to turn anti-clockwise. Is that clear? Now, I'm telling you that this bench does not turn. It is in equilibrium. Okay? This is in equilibrium. This bench is in equilibrium. Is that clear? So when the bench is in equilibrium, the moment caused by the tension, the anti-clockwise moment by the tension about this pivot should be equal to the clockwise moment caused by the weight about the same pivot. Are you clear about this? So why do we need to do that? I will tell you right just earlier, W equal to TL plus TR. So why must we do this so complicated? Okay, why? Because sometimes you are given the value, okay, you're given the value of W only. Okay, and this W may not be right in the center, it could be slightly to the right or to the left. So how are you going to determine what's the tension on the left and right? So you let the pivot be at the this left side here. You calculate the clockwise moment. Then you know that the anti-clockwise moment by PR will be the same. Can you find this value? So once you find this value, can you find this value? Is that clear? So sometimes you may be given only one force. And because you learn the principle of moment, okay, you learn the principle of moment, or when the body is in equilibrium, you're able to find the tension of the other by putting the pivot at one of the unknown. Because you put the pivot at one unknown, this will be 0. You're left with two forces. You know one force, you can find the other force. But just make sure that your clockwise moment is equal to your anti-clockwise moment. Okay, so if you're clear about this, can you give me a clap reaction? Can you give me a clap reaction if you understand this? How many you okay? Okay, so this is an example where the pivot is not very clear. You need to decide where you want to put the pivot. So the very easy way is to let your pivot to be at one of the unknown. So eliminate one of the forces. Then you calculate the others. Can? Okay, so let me go to the, so we have done with the explanation of moment, equilibrium. Okay, let me show you all some of the notes. Okay, so what is principle of moment? The principle of moment states that when the body is in equilibrium, the sum of the clockwise moment about the pivot is equal to the sum of the anti-clockwise moment about the same pivot. Okay? So, for what does equilibrium means? Equilibrium means the resultant moment is 0. Okay, the object is not turning. Okay, this one is called object not turning. Okay, then resultant force of the object is 0. What does this mean? Mean the motion remains the same. When it's at rest, it is at rest. When it's in motion, it was still in the same motion, in the same direction. Okay, so far? Okay, so we apply this equilibrium. Okay, so basically, your summation of motion is 0. Your summation of force is 0. Basically, this is number 1, this is number 2. Your net force is 0. Your net moment is also 0. So when this 2 is 0, your body is in equilibrium. Are you clear about this? Okay, when your net force is 0 and your net moment is 0, your body is in equilibrium. There's no change in motion. Clear so far? Okay, so for applying, I already give you 2 examples, the seesaw example, the simple one, and the not so simple one will be your swing. Okay, your swing. Okay, so I already given you these 2 examples. Let's continue. Okay, so we're going to talk about center of gravity. Okay, so there'll be a lot of questions that we'll go through next week to solidify this concept. Okay, but today I'm just talking about the theory, and I hope that I'm able to impress upon you the actual concept about moment and principle of moment. Okay, if I have been very clear about the moment and principle of moment, can you all give me a clap reaction? Okay, did I explain clearly something that you are able to understand much clearer from my efforts. Okay, if you are able to understand clearly, give me a clap reaction. Thank you, Zachary. How Ming Rui Hong, are you okay? Rui Hong, how about you? Are you all right? Okay, so we're going to finish up the last two part, which is the center of gravity and stability. Okay, so let me just go through very quickly. Center of gravity is where it's just an imaginary point where the weight of the body seems to be acting at a single point. Okay, so for example, you look at this iPad. Okay, you can see your face, right? There is weight throughout, correct? But there's only one point, okay, where the weight can balance. You see, where the weight can balance and will not fall. Okay, why? Why will it not fall? Well, this one not easy. I must find the point where it's balancing. Can you see now? Can you see that I'm balancing my iPad? Okay, so why is my iPad not moving? So can you imagine at the point of my finger touching my iPad, the center of that's where the center of gravity is, where all the weight of this iPad is acting on the finger. Okay, all the weight of this iPad is acting on the finger. So the perpendicular distance is 0. The iPad will not turn. However, if my finger is on the right side here, and the force is of the weight, the center of gravity is where the weight is, right? It is away from the pivot, or my finger is, it will cause my iPad to rotate and fall onto the table. Are you clear about this? Okay, so what is center of gravity? Let me show you some example. Okay, a center of gravity is a point where the object whole weight appears to act. Okay, so I give some example. If it's a rectangular shaped thing, if it's a regular mass with a uniform mass, or uniform density, you'll be right in the middle. So you put your finger there, you're able to balance because it doesn't cause the thing to turn, it can balance there. Okay, same thing for a cube, it's right in the middle, for a triangle right in the middle. Okay, this center of gravity, can you see here? Is right in the middle of the ring. Of course, you cannot put a finger there. Okay, but the center of gravity is right in the center here. Is that clear? Okay, so that is for regular shaped object with a uniform mass. Okay, uniform density. Okay, so if you want to put a force on okay, so your weight will all appear from there. Okay, what do I mean by that? If I have a box here, this is the center of gravity, this is a CG, your weight will be from this CG. Okay, when you draw all your diagram, your weight will be from this center of gravity point. Is that clear? Okay, so the weight of the object that we ever draw so far always come from the center of gravity. So if I put my finger at the center of gravity, it will not turn. But if I were to put my finger away from the center of gravity, can you see here? There is a perpendicular distance from the pivot to the force, to the line of force. Okay, there is a perpendicular distance. So therefore, this object will turn clockwise. Is that clear? Okay, so for irregular object like this, how do you find the center of gravity? Okay, first of all, okay, you balance the object, okay, onto a pin, like this, onto a pin. If the center of gravity is on the right side here, okay, if this is the center of gravity, I'm just giving an example. You have a downward force here, correct? If I were to extend this line of force, you'll be on top here. Your perpendicular distance will be from the pivot to this line of force. So this weight will cause this lamina to turn clockwise. If the center of gravity is the green dot, is that clear? So when you actually balance the lamina onto a pin like this, your center of gravity will be somewhere along this line. Okay, it will be somewhere along this line. Because if it's somewhere along this line, what's happening is your perpendicular distance will be 0. Anywhere along this red color line, your perpendicular distance will be 0. So it will not turn. Then you repeat the experiment with 2 more points. Okay? Eventually, you will see that the 3 lines that you draw will point to a center point. The center point here will be your center of gravity. So this point where the 3 lines intersect will be your CG. So are you able to conduct an experiment to find the CG of an irregular shaped object? Are you clear about this? Can? Okay, we are clear about this CG thing. Give me a yes reaction. Okay, we are clear about center of gravity. Give me a yes reaction. Zachary, are you okay? Okay. So now you understand center of gravity. So why do things topple? Okay, why do things topple? Let me show you. Okay, before we talk about stability, so let me explain why would something actually topple. Okay, so we talk about this item here. Okay, so let's say this is a regular item. CG will be right in the middle, correct? Okay, the CG is right in the middle. Your weight will be pointing down from the CG. So this is your CG. This is your weight. Is that clear? Now, okay, now, if I were to tilt this box slightly, okay, I tilt the box slightly. So let's say I draw a box like that. I tilt the box slightly, like this. The same box. Let me try my best. Okay, so I tilt the box slightly. How will it fall? Okay, how will it fall? Okay, just imagine I'm drawing very in proportion. So can you see? Now this is my CG. Okay, this is my CG. My weight will still be acting downwards from my CG. Are you clear about this? My weight will be still be coming down from the CG. Now in this case, there is a pivot here. Can you see? My pivot at this point, because the thing will turn either clockwise or anti-clockwise about this same pivot. Clear so far? Now, to find the moment, okay, to find the moment, we need to find the distance from the pivot to the line of force, the perpendicular distance from the pivot to the line of force of the weight. So in this case, where would this be? Okay, the perpendicular distance is from the pivot to the line of force. So this is your perpendicular distance. Okay, so the moment in this case is your weight times the perpendicular distance. And in this case, it will be clockwise. So are you convinced that the weight of this box will cause this box to rotate clockwise and back to its original position? Are you convinced about this? Clear? Okay, so where is the position of your CG and where is the position of pivot will actually determine whether does it stays goes back to the original position or will it topple. Okay, now let me draw another example. Okay, the same example here, but this time around, I'm going to slant it quite a bit. Okay, not very nice. Okay, so now where would the center of gravity be? It will be somewhere here, correct? Center of gravity is here. And where is my weight? My weight is down here. Okay? So this is my CG. This is my CG and this is my weight. Okay, where is my pivot? My pivot is down here. So in this example, okay, for this thing, now I turn it, I position it this way, where the weight now is on the left side of the pivot. Okay, so where would my perpendicular distance be now? It's now on the left side of the pivot. Okay, so my torque or my moment will be the same thing, weight times the perpendicular distance. Okay, and you'll cause it to turn anti-clockwise. So this box will actually topple anti-clockwise, and then you'll topple down. Is that clear? Is that clear? Okay, and that's the reason why this box will topple. Okay, so did your school teacher able to explain this to you, why things fall? Okay, I hope I able to explain properly to you why things will topple. All right. Now, before you go into stability, so to make the item more stable, what can you do? Two things you can do to make your item more stable. Okay, can we try to shift the CG? Think about it. If my CG is now lower, meaning that my box has a heavy bottom but a very light on top. So I use a green example. I use a blue example. Okay, so is my CG, I change the composite of the box. I make my CG now lower. Okay, so my CG is now lower, which is now here. Okay, my CG is now lower. What do you notice here? Do you notice that on all three examples, it will still goes back down to the same position? Okay, so to make something more stable, to increase the stability, one thing you can do is to lower your CG. Okay, how do you lower your CG? For example, if this is a cup, empty cup, if you fill some water below, like this, are you convinced that the CG now is no longer on top but below? So your cup is now more stable, harder for it to topple. Does it make sense? Okay, are you clear about this? Okay, if you can lower down your CG, your body will be more stable. Now, the second way to make things more stable, can you increase your base area? Okay, increase your base area. Imagine if my base area now becomes smaller. I use a blue color again. If my this whole thing is now like this. Is this very stable? Okay. Now if my thing is just like that, very small. Can you see? Is this more or less stable? You'll be less stable, correct? Okay, if it's just a blue color box, you'll be less stable. But if I have a very wide box, okay, my box is now very wide. Are you convinced that this will be much more stable compared to, oh, very hard to draw. Can you see? Is now my area is now very wide. The chance of it toppling is now also, can you see what I'm doing here? If it's very wide, yes, angle of tilt is the same. But if my base area is very wide, my CG is low, does this actually able to topple? No, you'll not be able to topple because my area is super wide. Clear so far? Okay, so to increase stability, first thing you can do is to either lower your CG. You design your item where it is heavy bottom, light top. Or you increase your base area. Okay, so can you imagine Formula 1 car? You realize that they are all very small because they want to make sure that your CG is low. Then their base is very wide. Okay, so that they don't topple easily. Okay, so when you are a Formula 1 car designer, you apply what you learned in Sec 3 physics, okay, to design your Formula 1 car to increase your stability. Is that clear? Okay, so let's continue. Okay, so two ways to increase your stability. I mentioned just now. Either you lower your CG or you increase your base area. Can? And the last 2 points I already mentioned just now. If your line of action of weight is still within the base, you'll return to its original position. But if it's outside the base, the object will fall. Okay, I already mentioned this just now. Okay, so the last thing I'm going to explain today will be 3 types of equilibrium. Okay, 3 types of equilibrium. So what does stability means? Stability means whether the object will able to return to its original position after being slightly displaced. So can you see the first one? Stable equilibrium. You displace slightly, it will still go back to its original position. Okay? You displace slightly, the weight, the line of action of weight is still within the base area, you'll come back to the original position. Clear so far? Unstable equilibrium is when you actually displace slightly. Now your weight is outside your base. Outside your base. Okay, it's now outside your base. It will fall. In this case, outside the base, it will cause it to fall. In this case, within the base, in this case, is within the base, you'll return to the original position. When it's outside the base, it will fall. Clear? So if you tilt slightly, your weight is now outside the area, base area, it will actually fall. This is called unstable equilibrium. Now, how about neutral? Neutral is like a cone lying down. Okay? The CG did not, okay, in this case, okay, in the first case, when you tilt slightly, the CG go out a bit. In the unstable manner, the CG actually drop a bit. But in the neutral example, the CG remains the same height. Okay, it remain at the same height. Then the line of action of the weight and the contact force coincide. So basically, if you are rolling, okay, we don't use a cone, very hard to imagine. If we are rolling a cylinder, okay, you roll it at the other angle. Okay, if you can you see here, this is the CG, correct? When you roll slightly, okay, when you roll slightly, you actually move to another new position. Okay, let me change color. You actually move to a new position. Your CG remains at the same height. Same height, number one. Number two, it is still within the same base area. So this is called a neutral stability. Is that clear? Okay, it is still within the same contact point, the pivot. This is the pivot. Okay, so it is still within the same contact point C, okay, which is the pivot. Are you clear about this? Okay, so that is all for today regarding this whole topic on turning effect of forces. We went through the basic idea of moment. We went through principle of moment. Okay, we talk about CG and we talk about stability. Okay, so are you all fully clear about the concept and what this topic is trying to teach us? Okay, if you are okay, give me a clap reaction. Okay, so for your acid question, number one, okay, write down the formula for moment. Two, what is the principle of moment? Three, what are the two factors to increase stability? Okay, how much you learned today? And how well Mr. Chu teach today? Okay, once you are done with the 5 questions, I call your name. Okay, you may leave the class. And if you have any more questions, for example, like how many you got more questions about other topics, you can always stay back and ask me. Okay, so answer this question. Once I call your name, okay, you may leave. How Ming, why you use the unit as your symbol? That's incorrect. Try again. Then you don't use the distance first. That's not what I teach you. So try again for question 1. Zachary, next time don't use M for moment. Okay, Zachary, don't use the word point, use the word pivot. And Zachary, you don't increase the body mass. You're supposed to increase the base area. So can you rewrite the first three answer again for Zachary? Ray Hong, can you write down the formula? Moment is equal to what? Then the distance, can you write down perpendicular distance? Okay, Ray Hong, your second question is correct. Yeah, so Ray Hong, you write down the first answer again. Hao Ming, you need to tell me about the pivot, okay, for your principle of moment. The pivot thing is important, so can you rewrite your pivot? Ray Hong, distance is small d, not big D. Right again. Okay, Ray Hong, just rewrite the number one. Okay, Ray Hong, you may go. You got no more question for me. Zachary, don't use NM. That is a unit. Okay, I don't know why you use the unit. So can you choose can you type moment or type tau? Zachary, you're increasing the base what? Okay, increase the base what? Okay, how many your question two is correct? No, you don't increase the base mass leh. Zachary, look at the screen. The screen got the answer. The screen got the answer. Try again, Zachary. Okay, Zachary, you got we have no more question, you may leave. How Ming, how do you change the height of CG? And how do you change the size of base area? Okay, when you increase stability, should you increase or decrease the height of CG? Should you increase or decrease the size of the base area? Okay, any more question for me? How Ming? Question number 5, what's your answer? Okay, thank you so much, everyone. Hope you all have learned something today regarding turning effect of forces, and I'll see you all next week.